Hi, my name is George, or Jorge, however you want to pronounce it. And I'm CTO and co-founder of MindCV. And I'm going to talk to you about democratizing machine learning and why we think it's important and our journey to what we're doing at the moment. So the first question that people ask is, why machine learning? And this may be very obvious or ubiquitous for a lot of you, but in case it's not, is to use the data that you have to make informed predictions. And this is important because a lot of us, even though we have been collecting data for a long time, we still make the decisions based on what is our gut feeling. And that is not bad, but you may also want to use the data that you have. Now, why democratizing machine learning? And this is exactly what we want to do. Can you guys hear me okay? Yeah. Okay, so why democratizing machine learning? The reason why we're doing this is because there is a huge demand for predictions, and there are very few true machine learning experts out there. And therefore, the funnel from people that want predictions to actually getting predictions is narrow. And there is a more profound problem to this, and is that the true machine learning experts, they are true experts in machine learning, but they are not experts on the domain where you're actually getting the predictions from. I myself, I work making predictions in healthcare, and I barely know the name of the bones. So I'm not really someone that should be delegated with the responsibility of making predictive models within healthcare. It should be the doctors, the physicians. And likewise, there are many domain experts that are not necessarily machine learning experts, but they do have profound expertise in their domain. Now, the beauty of Python is that it allows a lot of people not necessarily to be developers by profession, kind of like what Christian was mentioning earlier today. You can be anything, but you can still be a developer. And that's the people that we want to encourage to use the data they collect to make informed predictions. So the simple way to democratize machine learning is, of course, to build tools that allow any domain expert to actually use this data to build machine learning models and really understand how they can use it for their specific problems. That way, the demand from predictions to actual insights and predictions is a kind of one-to-one. The first step that MindCV is taking is to democratize it to the developer. Again, as I was telling you before, you may not necessarily be a developer by profession, but you can still learn how to code. Or you can be a developer by profession, but you can develop all of your career around a specific domain. And that may be more important than actually becoming a data scientist. In our opinion, data scientist is kind of a role that can be specific to people that want to develop tools for others rather than for a specific industry. Now, why developers? Well, developers are awesome. And we build shit, we get it done. And a lot of the products that we see today are built by developers, not by machine learning people. And we think that developers, just by the nature of the developer, we're the ones that build the means to actually produce data and organize it, and therefore we can aggregate it. And that is the key element to actually doing machine learning. The machine learning element, it cannot do anything without the data. And we engineers and developers, we can actually put this data together and fit it in. So we want to change the paradigm from building models to actually think of what data is important, and then delegate the machine learning part to a system that can kind of like use the best practices at the moment. Now, there are many more developers than data scientists and machine learning experts. There's probably 1,000 or more developers for every true machine learning expert out there. So how do we do this? Well, we abstract the complexity of machine learning and data science, and we provide it through an interface that is simple. And all of the complexity can be replaced and kind of like evolve as machine learning evolves as well. What is important? Well, if you are delegating machine learning to a system, then you need to be able to trust the system. The same way that you'd be able to trust a data scientist or a machine learning expert. More importantly so, machine learning is evolving to the point that it really gets quite complicated to understand what it's actually doing. And if you are delegating important decisions to a system that is supposed to be intelligent, then you should at least be able to understand and trust it. So we actually believe that that is the key ingredient to democratizing machine learning. Not only making it very simple, but also being able to understand what's happening. Now, I'm going to talk to you a bit about our approach at MindZB. And the reason why I wanted to break this into two is we encourage people that do know machine learning to think more about building tools that are meant for others so that others can actually implement machine learning within their infrastructure. And feel free to copy our approach and even expand it. MindZB is open source, so you can go to MindZB and play around with it. So MindZB is driven by three simple goals. The very first one is to make it frictionless. And we love Python, again, because it is easy for anyone to start, and then you can grow your complexity as you grow your understanding of your problem. Now, we want to provide an API that is easy enough that anyone that knows just the very basics of Python can actually use. And therefore, is to be able to build and use machine learning models with just one single line of code. The second goal that we have is that it has to be explainable. Again, as I was describing to you, that is the key ingredient to actually be able to democratize machine learning. And what is explainable for us? Well, it has to answer these questions. Why this prediction, if you get one? And why not something else? Why is this model working? And when is it working? When can you trust it and when you cannot trust it? And more importantly, what can you do to improve your predictions over time? And the third thing that we want to make sure that is core to what we build is that machine learning really evolves. So what was the latest thing a few months ago wasn't even invented 12 months ago. And it continues to be like that. So we want to be able to, even though we provide you a very simple interface, behind the scenes we want to keep it as up-to-date as possible so that you can still rely on the latest of machine learning findings without really having to think about them. Well, so if you want to try MindZB, well, it's a Python module, so you can install it with Python 3, and that's it. Actually, that's not it. I'm kidding. We still have a lot more. So what's coming this month, and this is what we wanted to share with you. In case you're interested, we can release to you a beta release. So approach me after this, and I'll get you into the list of what we're releasing this week. Over the past 3 months, we had a lot of feedback from the first version that we released, like the pre-release 1.0. And what we wanted to do was to incorporate a lot of the learnings that we had, and these are some of them that we're releasing now in this MindZB version 1.0. The first one is a cleaner API to support many more data types. And right now there are two tendencies in what is the backend of machine learning, TensorFlow, PyTorch. So we made it so that you can pick. And that is explainable. And lastly, that is ready for production. So kind of like what we released before was something that you could toy around in your laptop, but not something that you could put in production. So let's start with a cleaner API. So initially, you just kind of like instantiate MindZB, and you tell it what you wanted to learn from, and what you wanted to predict, how you wanted to call it. But it will stay like that. So we introduced a predictor object, and the beauty of this is that now the predictor object can be moved around. So even though you may train it in a computer or in a computing cloud, you can move this around into like an embedded device or to your own server. So it works like an object that can be transferred from like different instances. As well as it can be run in kind of like a Kubernetes, and depending on your needs, you can scale it up and down. The third thing is that initially we were working only with numeric and categorical columns. So long you can transform your data into a table, and those tables were either numeric or categorical, we could work with them. In MindZB version 1.0, we kind of like expanded that a little bit. So your tables can be numeric, and that could be like either integers or floats. Categorical, they could be a single category or multiple categories. They could be times and dates and whatever representation of those are. Binary as images, audio, and video. And sequential as text or any combination of the previous ones. And we started to work with explainable artificial intelligence. When you produce a model, right now, MyZB, as you have it, you can't really get any explanation, and that's what we're doing in this new release. So you can, once you have a predictor, you can ask it to explain quality. And this is only the beginning of what we're doing with explainability. We believe that before you can actually explain something, you have to really explain the quality of what you're being produced, or the information that is being presented to you. So the second thing is, once you have an actual prediction, you want to do the same. You want to know, how good is this prediction? And this is very important because when you're using neural networks, they're not deterministic. The initial state of a neural network is random, and therefore what it can learn in one single iteration, or like in one go at learning, may vary every time you train it. And you want to know, how good is it with like something that is intuitive to anyone, regardless of their capacity to understand machine learning. So let me explain this a little bit more. When you train something with MyZB and you go and explain quality, it will give you quality metrics that are intuitive to you, but are actually meant for you to understand if the data that you're feeding into your problem is data that you can actually rely on, and how can you fix it. So the first thing that you can actually understand is, how consistent is your data, as how much error is in the data that you have. And MyZB will take it out when it trains it, but it makes you aware of this. The second thing that it does is it try to understand, is there any redundancy in your data, either by rows or columns? And even though MyZB will fix those redundancies, it keeps you aware of this. The second thing is the variability. So is there a lot of bias in your data? And this is crucial to machine learning because a lot of the data that we collect may be inherently biased towards something. And we want to inform you about this crucial insight, because if you don't fix it, your predictions will be biased. Is there a lot of noise? And no variation at all. That means that your data cannot actually produce any meaningful information to learn from. How complete is your data? And lastly, once you produce a model, what is the quality of this model? So what values it's actually really good at learning and at predicting, and what values it's not that really good at predicting. Because you should really understand that when you're getting a prediction, say for instance, you're trying to build a system that predicts cancer, you want to trust when you can actually tell a patient that that patient has cancer. Or any sort of prediction, you really want to know how much you can trust it. So MyZB, when it actually trains something, it will tell you, well, you can actually trust with a certain degree of confidence, and you cannot trust it within these values. And these are the reasons why we think that you can't. Right now, it points back to the quality metrics that it observed before. Now, the same thing happens once you get a prediction. So you have your predictor, you can kind of understand why it's working and why it's not working. But also, when you have a prediction, you want to know not just the predicted value. And what I was telling you before is crucial to this. The more we move into artificial neural networks, the more one has to understand that the results that we're getting are stochastic. So what we want to know is, this predicted value, how certain am I that this is the value that I want to get? And what we provide to you right now in this very first version is, okay, well, this is the value that we think is a prediction. The certainty that we have that that value is the value that you're looking for. And also the distribution of all the possible values. And then you can make your decision for that. Now, the third thing that it's important for us is that once you build something with MyZB, you can actually move it to production. So this new version of MyZB is something that you can install, again, with the same pip install MyZB. And you can run on your desktop, and you can move models around. But there's also a MyZB server that allows you to move stuff that you've trained on your computer. You can actually delegate training to MyZB server, but it will also expose it on an API. And it comes with Colin, so you can scale, and you can have authentication and all of the other gateway API niceties. We're providing a very simple MyZB graphical user interface so that you can visualize these explanations. Even though when you do MyZB.explain, it will explain it to you in the terminal. We want to provide you visual insights into these explanations. And of course, we know that Python is very nice when you're having the backend, and the front end is not that real. So we provide ASICs for other programming languages. Okay, now this is really it. Please come back to me if you want to try the release that we're having next week as a beta tester. And yeah, if you have any questions, feel free.
Okay, thanks. That was really great. I have actually two questions for you. That seems like a lot of work to do, but it's still open source and free to use. Where do you make money on? What do you make money on?
Yeah, our investors ask us the same question all the time. We don't know. We don't have a clue. I didn't send the link to my investors, so it's fine. The question is, this comes out of a research that we were doing at Berkeley. So UC Berkeley invested a little bit of money, and that's how we released the first version. And we were lucky to get into probably the coolest investors you can find, where they allowed us for 6 months to release this open source and really learn a lot about it. And then starting Q3 of this year, we're going to understand what are things that bigger companies want. So we will still produce this core features that I'm providing for you for free and open source. And then our intuition is that bigger institutions like banks, big healthcare organizations, they have scalability needs. And machine learning, when you are doing it at like a medium scale, it works fine. But once you want to go into like thousands of transactions per second, and that type of data throughput, you still need to do some heavy engineering in the backend. And those are things that we're probably going to sell. But the candid answer to the question is we really have a fucking clue.
Okay. And the second one, are there any success stories about using your service, or is it just people try it out and then forget about it in 2 weeks? Or are there any success stories with MyCB, with somebody using MyCB?
Yeah. So the first person that used MyCB was University of Pittsburgh, and they have a very interesting use case. They taking heart reading data from patients in a hospital, usually patients that are old. And one of the high risks for these patients is when they stand up from their beds, they fall down. And this happens because they have what is called a hypertension attack. So essentially the heart pressure boils down to dropping. And when they stand up, they experience dizziness and then they fall. What they do with MyCB is that they fit in the time series data of the heart readings. And MyCB can predict when the patient is about to stand up. And it can also predict if they will experience a drop in pressure. That's one of the use cases. We have people optimizing. There's like this company that does self-driving vessels, and they want to optimize fuel consumption. Now, granted, they're a machine learning-based company. I mean, they do self-driving stuff. But for specific problems, it doesn't really make sense to hire a full data scientist to do it, such as like oil consumption and this. So they use it for that type of data. We have it for insurance. So people that want to predict what will be the chronic conditions of a population in the next 12 months time. MyCB has been installed, even though in this kind of like early release, more than 30,000 times. So the number of use cases that we have are known to us. And a lot of what we want to start doing is in this community is really to understand where can we be better at something that a lot of people want. Since it's something that you install on your computer, we only know what you tell us. So if you have an interesting use case and you would like to squeeze something more out of MyCB, please feel free to send us an email.
Thank you. I have kind of a big question, so I expect some kind of general answer. As I see, you haven't mentioned anything about what's under the hood, like what algorithms do you use? Is it just neural networks, deep learning, other algorithms? Does it use some sampling? Does it use some statistics, data filtering? Like in general words, what does MindSDB uses under the hood, if you can?
Yeah, so the research that we did was that you can generalize machine learning by treating it by columns, so data type driven approach. And so long you can convert your data into a relational data store, you can turn whatever query into a single table. And each table will have different columns. Those columns will have different data types. And that's why it was talking about data types. There are canonical ways to build vector representations of each of those columns. If you have a text, all you want to care is if the value is present or not. If you have a number, so it turns into like a two-dimensional vector. The first one is the actual value, the second one is null, not null. If you have time information, then the vector becomes a little bit more complicated because you have like month, day, year, and whatnot. If you have text, then it can be either categorical, so then it becomes like a vector of whatever number of categories you have, plus if it exists or doesn't exist. If it's a full text representation like sequential data, then your vector representation, there are state-of-the-art algorithms to convert whatever text into like a vector representation. Right now we use GRUs, and we use the last hidden state for that. And that may change, but that's the beauty of using MindSDB. You don't really have to care about using the state-of-the-art. That's our job. We pick what is performing the best at encoding data. And same thing with video and images. So once you have like a vector representation for your columns, then you also want to understand what is the vector representation of your target. And whatever you put in between can be a mix of things. And MindSDB tries a few. So essentially, depending on the statistical information that it finds from all the columns that you have on your target, it generates a few candidate neural networks. And once it trains the neural networks, then it picks the ones that performs best.
It's always a neural network, right? It's always a neural network.
It's always a neural network there, yeah. And in the last stage, what we do is, since it's always a neural network, and depending on your target, you may have like a probability distribution at the end or not. Most likely you won't. Then at the end, we just do some bias inference so that we can actually get the probability distribution of your prediction. We experimented before as well with probabilistic neural networks, but the performance isn't that high. So it makes sense to just use regular neural networks in between, and then at the end have a probabilistic layer that will give us a smooth probability distribution for whatever it is.
As I understood, the user just fit in the data and they get some predictions on the future data that they fit in, right?
Correct.
You mentioned that users can use like PyTorch or something? TensorFlow, yeah. As I understood, the user should specify their model on which they use to predict. Or the MindSDB have some generic model that fits to every kind of data. Because it's hard to have a generic model. And that's the problem that some companies like Data solve. They have like 100,000 models for different kinds of data, and they just try many models to see which one works best.
Yeah, and it's related to the same question that you asked. So again, Data Robot uses a lot of classical models for what can be learned now with neural networks. And there's a trade-off that you're making. Neural networks are actually really good at learning nonlinearities within data, and therefore they outperform most of the classical models, so long you have enough data. So MindSDB leverages this, and we do generate a few proposed neural networks for the target, and we try them, and we train them, and then we pick the one that is the best. And then on top of that, as I was describing, we use some probabilistic learning algorithms. But we don't use any of the other classical models, which is like random forest and that Data Robot uses.
How do the users use PyTorch with your system?
Yeah, you can set a configuration where you want either a PyTorch backend or a TensorFlow backend, but you don't get to specify the model. Yeah. So essentially, MyZB will generate those neural networks, and they will run either on PyTorch or TensorFlow. So whatever your flavor is, and whatever, because if you already have machine learning infrastructure running in the cloud, you may already have like services that have like TensorFlow already installed and whatnot. So we allow you to pick which one of those you want to use as a backend.
Yeah, I've got a small question. Do you collect any statistics on the accuracy of the predictions that the users get that the model optimized to be?
So the last stage of, or the best practice at the end when you have a trained model is that you run it through some validation sets. And that's what we do. Oh yeah, sorry. You were not able to hear me.
Okay, I have a question about the speed and performance of the library.
Yeah.
So, you mentioned that you are using BERT embeddings, right?
Sorry?
I heard it correctly. You mentioned that you are using BERT for the text representation, converting text into vector, right?
GRUs. So GRU is a subfamily of LSTMs.
I see.
And what we do is we take the last hidden state of the recursion, and that is a vector representation. So BERT builds upon like different methodologies, a lot of them based on recurrent neural networks, but they have pre-trained models. We don't use BERT.
So if this approach, for example, if it works slowly for me, because it's LSTM-based approach, as we have found, it works quite slowly on a lot of big texts. So it works better on short text when you don't have tens of kilobytes of text. And if it's slow, what do I do?
And that goes back to the question of what I can
Convert, use a different integration.
So BERT is built on top of TensorFlow, and is by Google. And they use different methodologies. And you're right, if your recursions are quite large, then depending on how you build the embeddings, then you can kind of like optimize this a little bit. Right now, we have no one has come to us with like a use case like yours where you have like to analyze a full document. But the optimizations will happen based on whatever backend you use at the moment. So if you use TensorFlow, then you can use the distributed training for TensorFlow, and then it will be a matter of having Kubernetes or whatever you want to do to scale up the training. And likewise, PyTorch has a distributed training kind of like niceties. So depending on which one you choose, you can squeeze those. As to the methodology, again, right now we only use encoders based on recurrent neural networks. But if you have a use case that is interesting, like the one that you clearly have, then we're happy to work and see, okay, if the data is big, let's use a different type of encoder. Or, you can break it down into paragraphs, encode each paragraph, and then do an encoding on top of that, so you can distribute it. There are different methodologies, but what I'm trying to communicate to you is the current one that we use is LSTM and based encoders, and the optimizations that you can make are based on the backend that you pick, and the capabilities of that backend to scale in a cluster for training.
Thank you.
Question: can you train the compound model, for example, big text and image?
Yeah.
In one data set?
Yeah, you can.
What model you use for this?
Again, what we'll do is it will take the column that has the images, it will build a vector representation of that image. It will take the other column that you have, whatever vector representation it has, and then at the end it just takes all of the vector representations, concatenate them, and feed them into a full connector.
And do you write on the code, or you can host your, for example, host your software on the GPU server or so on?
Yeah, that's a good question. So that's one of the things that we're releasing in this version 1.0, which is to allow you to, once you have a model, or a predictor as we call it, because a predictor is a combination of things, not just a single model, it's a combination of models. Once you have a predictor, then you can move this predictor around into like, let's say you train it into a giant computer with a whole bunch of GPUs, but once you want to move it into production, you may want to have it embedded. then you can move this train predictor around. So you just can export it. It gives you a zip file, and then you can just move the zip file around. And the other thing is you can also install MindCP server. Again, it is going to be a pip module, so pip install MindCP server, and then you can push predictors that you train in one device to another.
And do you provide JavaScript?
Sorry?
Do you provide JavaScript clients for your scheme?
So we're providing the API, and we have an SDK that we use for the graphical user interface that we are providing as well. So we're releasing those SDKs, but the idea is that people can help us produce other SDKs for other programming languages.
Thank you very much.
I have one more.
Okay. I guess I have a question about the research. So, I think that the key feature of your talk is some kind of proof why this particular prediction was against the user. So it's interesting how we can give this answer, this proof of prediction and will be useful kind of data. For me, it sounds like you process and a lot of data. Based on that, make some decision, prove this for you, but how you can see that this prediction is really reliable.
I'm having trouble understanding the question. So let me see if I get it correctly. The question is, how do we build the explanation?
Yeah, how it's how user can get this proof of prediction.
Yeah. So this is a work in progress, and what we're releasing at the moment is 2 or 3 quality explanations. The quality explanation of the data that you have, and this is just going through all the data that you provided and tries to find those different quality dimensions, and it will try to inform you. The second one is the quality metrics that we have on the model, and this is actually not that complicated. It just goes through all of a subset. In this case, we call it validation sets, and it runs it and will break it into buckets as to depending on your prediction, where within the histogram of your prediction is failing, and it will try to map what are the quality metrics that are associated to that part. So say for instance, your data doesn't have a lot of variance in a specific region. This is something that you identified in the data analysis. And intuitively, you will know that your model may not be very good at learning from that region of the data. But if it happens to be the case, then we can go back and point out to what is the quality metric that is not performing or is not helping you learn that well within that region. And this works for when your target, the variable that you want to predict, is either numeric or categorical. And a little bit with text, if you have a way to find a percentual hash of your text, because then you can break it as well into a histogram. And with images, it's a little bit trickier.
And again, that's why this is work in progress. And what we're releasing right now is a way for you to understand what regions of your target is not learning very well, and then mapping that to what we analyzed before as to what were the quality issues that we observed initially. And lastly, when you get a prediction, right now what we do is definitely what I explained to you. We train the neural network, but then on top of this, we do some probabilistic analysis of that predictor. And we try to understand what is the probability distribution for all the possible values that your predictions could have, given that your model predicted this. So if you think about it, the latent state will be the input, and then your observable state will be the actual prediction.
Have 5 minutes left.
Thank you. The other thing I wanted to know is whether you choose a different type of network architecture depending on the data input. For instance, do you use convolutional neural networks for image input as your first choice, and then different types for other data types? And do do you use only supervised learning, or have you experimented with reinforced learning or other types of neural networks that are more experimental for now?
Yeah, that's a good question. So right now we don't do reinforced learning or unsupervised. And that's absolutely right. What we do for learning is based on the input column. However you want to build the embedding, the vector representation defines what type of neural network we use. So for text, we use neural networks. For images, we use convolutional neural networks. And then we use autoencoders, so we can keep them in wait state. And then for the other ones, such as time series and other types of data, we have different ways. Actually, time series, there are different methodologies to like extract rich features from the time series. So we try a few of those, and then we pick the ones that yield the highest R-squared. I try to predict it very well. And then once you have that encoded state vector representation, then we use fully connected, which is the aggregation is. Yeah.
Okay, since we have no more questions, I would like to thank George for your work here and for joining us in this conference.
Thank you
very much.